Welcome back, everyone. Professor Cameron here. Now, what we're going to be doing this week is what we call three-axis milling. Everything we've done up until this point has been what we call 2.5-axis milling. Now, I'm going to pull up my great simulation software here and show you guys the difference. 2.5-axis milling is milling in essentially three axes, but it's only moving in two axes at a time. So in our situation here, we're just doing a simple square cut, right? Our cutter is going to come along the top, cut this, and then it's going to come down. And then it's going to cut a level here. It's going to come down. It's going to cut a level here. It's going to come down, cut a level here. It's only moving in two axes at a time. So it's not cutting a sloped profile like this. Our cutter is only moving two axes and then adjusting, cutting two axes. On three axis, the cutter is actually moving in three axes at any given time. And we do this to cut curved profiles and more organic shapes, right? So for this, our cutter will actually come in and move through all three axes, X, Y, and Z, at the same time. And that's the primary difference. Now, as far as programming goes, it's more or less the same. But there are a few things we need to pay attention to. So what we can do is start the programming on this piece here. Now this piece, it's essentially a dished cutout, right? Very similar to kind of like a bowl shape. So what we're going to do is we're going to dive right in and start the programming for this. Now we're going to start the programming for this very similar to how we do everything else. We're going to go to SolidWorks CAM. We're going to do define machine, and we're going to mill in inches. We're going to set our coordinate system, part bounding box, and we're going to select this corner here. We want to adjust our axes so that this is the X. This is our Y, and our Z should be sticking straight up, and that looks pretty good. Next, we're going to go to Stock Manager, and for this, we're not going to add anything extra to our stock. We're just going to cover cutting out this bowl shape. So our stock size for this model is going to be 5 by 3 by 5. We can go to Setup, and here's where it varies a little bit. We're going to do the same thing that we always do. We're going to select the top surface, but then we have to come down here and select multi-surface feature. If we don't, SolidWorks CAM will not recognize this bowl, and it won't give you the option to extract machinable features and generate operations plans. So we're going to select multi-surface feature. And then for this, we're going to select area clearance Z level and select OK. All right, so that looks pretty good. What we're going to do is extract machinable features next. It's recognizing this bowl area here. So now we can go to generate operations plan. And you can see what it's putting in is an area clearance with a 3/4 inch flat end mill. What that's going to do is it's going to hog out the bulk of the material in here with a 3/4 inch end mill. Next, it's switching to a 1/4 inch ball nose. And what that's going to do is it's going to refine the shape to create a more uniform, a smoother surface. So let's go ahead and just see the toolpaths for these while we're before we go ahead and get everything set up here. And we can see how this toolpath is going to work. So what it's doing is it's coming in here, hogging out the bulk of the material, and then with the ball nose, it's going to smooth off that perimeter. And let's go ahead and simulate this, and we can see how this is going to work. So it's coming in here with our 3/4 inch end mill. And it's just going to hog out this material. And you can see the surface that it left behind. This sort of stepped surface here. And this is just a result of how the flat end mill can cut a curve. You know, it cuts it roughly to shape here. And then we can see the effect of the ball nose. This is going to come in and this is going to smooth this out for us. And you can see it's smoothing out this surface, leaving a uniform, smooth, flat surface. And then that's going to get to the bottom. And that's going to cut it mostly to shape for us. Let's go ahead and cut this back in half here. And that did a pretty good job. Our sidewalls here are nice and smooth. But once we get down here, it's a little janky. It's a little janky. And some of this is a function of the rendering, and some of this is a function of the programming. So if we were to cut this right now, it wouldn't look nearly this bad. One of the things you'll notice when we program is that the program simulation often looks like it leaves a worse surface finish than the actual finished parts do on an actual mill. So we're going to keep that in mind as we go ahead and program the rest of this. But let's go ahead and tweak our parameters here to get this a little more finished looking and something that we could run on our machine. So let's first go back to area clearance. This is the one that just hogs out all the rough material, and we're going to edit this. Now, our tool, we're going to leave this at the 3/4 inch 2-flute end mill. That's fine. For feeds and speeds, we're going to go ahead and edit this. We're going to assume we're using a carbide tool in aluminum. So if we go ahead and do the math for that, that's going to be 4 times V divided by D. So that's going to be 4 times 600, which is the surface speed for carbide in aluminum, and then divided by 0.75. Now, let's see here. That is going to give us a spindle speed of 3,200. And then our feed rate is going to be 3,200 times 2 thousandths times 2 teeth, which is going to give us a feed rate of 12. So that looks pretty good. For pattern, we're going to leave this all the same for right now. In later videos, we're going to cover step over and how that affects our cutting speed and surface finish. But for right now, we're going to leave this alone. We'll touch on this in the next video that we do. Area clearance. So you guys saw when let's see if we can't do this here, how we left quite a little bit of material at the bottom. It left a pretty thick pad right at the bottom of this bowl. So what we're going to do is we're actually going to set all of these to 0, and this is going to cut it as close to shape as possible. It's not going to leave any excess for us. And the reason we're doing this is because we want to minimize the number of tool operations that we have to put in here. We don't want to have to come back with secondary operations to go ahead and cut off this excess material. We're going to try to do this in 2 operations. Maximum cut amount, this is going to be 50 thousandths. And same with cut amount, 50 thousandths. And C plane, our rapid plane is going to be 1 inch from the top of the stock. And then that's all we have to adjust for right now. We can go ahead and click on it. It's going to ask if you want to regenerate toolpaths now. We're not going to bother because we're also going to edit the Z level, the ball nose path. We'll regenerate them both at the end. So let's go ahead and do our same adjustments with the Z level here. We're going to edit the definition of that. Now, a 1/4 inch ball nose, that's a very small ball nose. What we're going to do is we're going to bump that up to something a little bit more robust. We're going to go to our tool crib here, and we're going to use a 3/4 inch 4-flute ball nose. Select. Yes. So 3/4 inch 4-flute ball nose, we're going to go to feeds and speeds, defined by operation. Our spindle speed, it's going to be the same. We're going to assume we're using a carbide cutter. Our feed rate is going to be a little bit different because it's a 4-flute ball nose. That's going to be 2 thousandths times 3200 times 4. So that's going to give us a feed rate of 25. We're not removing a lot of material with this, so we can actually move this cutter pretty quick through our part. Z level, we're going to leave this all as is. We just want to check our cut amount and make sure that that's 50 thousandths. And C plane, 1 inch top of stock. And then we can go ahead and click OK. Now we can go ahead and regenerate these tool paths and see how these look here. All right, so that looks pretty good. So let's go ahead and simulate this. We'll see how this looks. So that's cutting through. It's removing all that material for us. And then we're going in with our 3/4 inch ball nose. And that looks pretty good. So let's go ahead and take a cross section of this. All right, now we still have this pad here, so let's go back and check and see what we did. That should be in the area clearance. There we go. That looks a little bit better. It wasn't, looks like it didn't update for the new parameters that we put in. There we go. Chop the bottom. Now it's coming through here and it's just cleaning up all these ridges that we had left behind from the 1/2 inch, or from the 3/4 inch flat end mill. And that looks perfect. That looks pretty good. What I did do in the area clearance is I checked use global facet deviation. What this does is it's just a different way of SolidWorks interpreting the curved surface. Make sure you have this checked, and then make sure you regenerate your toolpaths. That was the issue I ran into on the first pass, is it didn't regenerate for the new feeds and speeds and depth of cut. So when we run this again, we can jump right to the end here. That looks pretty good. We have a nice smooth cylinder wall, and it's cut all the way down to the bottom, which is what we want. So at this point, our tool paths are complete for this, and this is a nice, simple two-tool program. What you guys can do now is you can go ahead and save this model. And if you guys have any questions on this process, please let me know. And as always, have a nice day.